Okay, so in part two, we're going to continue talking about basic concepts in probability. And this time we're going to be talking about calculating probability. And we're going to move on to the addition and multiplication rule. So up until now, we've only talked about or spoken about probability of simple events. Remember that a simple event is a single outcome that can't be broken down into simpler components. Okay? So for example, here we've got a table that includes the family histories of about 318 patients that were diagnosed with bipolar disorder, or BPD, that either had an early onset, meaning they developed the disorder at 18 years or younger, or a later onset after the age of 18. Okay, so we'll see this table come up in several examples here, but we have a total number of participants of 318. We've got our early folks, our folks with early onset bipolar disorder, later onset bipolar disorder, right? 141 early onset, 177 later onset. And then we also categorize them based on whether they have a family history of mood disorders, no family history of mood disorders, that's negative, a family history of bipolar disorder, a family history of unipolar disorder, or unipolar and bipolar. Okay, so that's the data that we have to look at and to practice with. So simple events are single outcomes that can't be broken down into simpler components. So what if we want to look at the probability that a person will have a late onset bipolar disorder? So that's a simple event. That's a single outcome. Late onset bipolar disorder, that's 177 individuals. Okay, out of 318. What is the probability that a person will have early onset BPD? Well, that's again a simple event. That's a single outcome. That's 141 individuals, okay, out of 318. So to calculate these simple event probabilities, we'll use the formula for relative frequency probability, right? Where the probability of A is equal to the number of times A occurred over the number of times the procedure was repeated. Okay. So the probability that a person will have late onset BPD, that is 171 of our sample out of 318. So probability of late onset is equal to 171 divided by 318, which is 0.557. Remember that 3 significant digits. Right? We round off to 3 significant digits. What is the probability that a person will have early onset BPD? So probability P early onset is equal to 141. There's 141 early onset folks, divided by a total of 318, which gives us 0.443. Okay? So that's how we calculate simple event probabilities. But sometimes we are looking for compound events. A compound event is when an event combines 2 or more simple events, okay, where we have 2 or more outcomes that we're looking at. So, for example, if in the same study we wanted to look at the probability that a person will have late onset BPD or have no family history of mood disorders, another possible question with compound events is what is the probability that a person will have early onset BPD and no family history of mood disorders? How we determine or calculate the probability of each of these compound events, each of these questions, is going to be greatly determined by the or the and conditions in the question. Okay? We're going to have very different approaches to an or statement of a compound event versus an and statement. So let's look at the condition of the or statements. Okay? Probability of A or B occurring. In that case, we're generally going to use something called the addition rule. If we're looking at the probability of two or more events where A or B, we're going to use the addition rule. So the addition rule is noted as P, A, or B. And it is equal to the probability that in a single trial, event A occurs or event B occurs, or they both occur together. Okay? It includes all possibilities. A occurs, or B occurs, or they occur together. And it's very important that to find the probability of A or B, we have to add the number of ways that A can occur, and then add to that the number of ways B can occur. But we have to add it in a way that every outcome is only counted once. Okay? And so P of A or B is equal to that sum divided by the total number of outcomes in the sample space. Okay. So another way of putting this is probability of A or B, P, A or B, is equal to probability of A, PA, plus probability of B, PB, minus the probability of A and B occurring together. Okay, so that we don't count that twice. Okay. But again, this is all in one trial, all in the same trial. So we have this issue with A or B questions, that sometimes A and B overlap and sometimes they don't overlap. Okay? So over here, we have conditions where A and B don't overlap, right? We have all the ways that A can happen, all the ways that B can happen, and there's no overlap, right? In this case, we talk about A and B being mutually exclusive, right? They are also described as being independent events. One doesn't depend on the other. So another way to say it is that they are disjoint. They do not overlap at all. And if that's the case, if A and B do not overlap at all, it makes the addition rule much simpler. We can determine probability of A or B is equal to simply the probability of A plus the probability of B. Okay. However, sometimes A and B do overlap. In that case, they are not mutually exclusive and they are not disjoint. And that's the condition where, in order to get P of A or B, we have to add PA and PB, but subtract out the overlap, the area of overlap, the PA and B. Okay. And that's so that we're not counting A or B twice. So let's do an example. Now let's look at a different table of data. So here we've got a table that includes 550 job applicants, and they all underwent drug testing. Okay, and they're divided up into subjects that use drugs and subjects that do not use drugs. So some people, and then the other way they're divided up is people who got tested positive for drugs, and people who tested negative. So notice that there are some people who used drugs and tested positive. That's a true positive test. Some people do not use drugs, but they still tested positive. We call that a false positive, right? Sometimes people, based on the foods that they eat, they get a positive test results. If you really like poppy seed bagels, right? Those little black seeds on bagels, they are actually from the opium plant. Poppy is from the opium plant. And so if you eat enough poppy seed anything and you do a drug test, you might test positive for opiates, right? For basically heroin. So that's a false positive. The person does not use drugs, but they still tested positive. And then among the people who test negative, right, 5 of those people actually did use drugs. That's a false negative, right? And then 480 people who don't use drugs tested negative. So that's the data we're looking at. So let's answer an example. If one subject is randomly selected from those 550 subjects in that drug testing study, let's find the probability of selecting a subject who had a positive test result or uses drugs. Positive test result or uses drugs. Okay. So the total number of people who were tested positive were this is that column right here. Total number of people who test positive is 45 of true positive, 25 false positive. And the people who use drugs, right? That's the other condition. The people who use drugs are the 45 who tested positive and 5 that tested negative. So we do have overlap, so we have to be careful. We have to be careful that we don't count people twice. So, the probability of a positive test or using drugs is equal to probability of a positive test plus probability of using drugs minus probability of positive test and uses drugs. Okay. So, probability of positive test is 45 plus 25 divided by 555. Probability of uses drugs, right? That's 45 people who test positive and 5 people who tested negative, right? So 45 plus 5 over 555. And then we have to subtract out those people who use drugs and test positive because we've already counted them. So we subtract out 45 over 555. And that gives us, if we do this math, that gives us 0.135. That is the probability of, out of those 550 people, we randomly select somebody that they either have a positive test result or they actually use drugs. So let's do another example. Let's use our bipolar disorder group for data for that. So what is the probability that a person will have late onset bipolar disorder or no family history of mood disorders? Okay. Late onset bipolar disorder, that's this group right here, or no history of mood disorders. Okay. So what we're looking for is the group that has late onset bipolar disorder. There's a group with no family history of mood disorders. But again, we have to be careful because there is overlap. There are people who have late onset BPD with no family history. So the probability of late onset or no history is equal to the probability of late onset plus probability of no history minus the probability of late and no history. So the probability of late, we had 177 late onset out of our 318. So 177 divided by 318 plus our no history. The no history, negative history of mood disorders, that's 63 participants, including early and late. So 63 divided by 318. That gives us our probability of no history. And we have to subtract out the group that has late onset and no history. That's 35 people. So we have to subtract out 35 divided by 318. So that gives us, if we do that math, that gives us 0.645. That is the likelihood of having somebody with late onset or no family history of mood disorders. Okay. So let's talk for a minute about complementary events again in the context of the addition rule. We talked about complementary events. Remember, a complementary event is when the complementary event is in the event that a condition does not happen. Okay, so we have some event A, and then there's times where A does not happen. Okay, so the complement of event A is denoted as A with a bar over, and it consists of all the outcomes in which the event A does not occur. So by definition, complementary events are mutually exclusive. Okay? Complementary events behave like this. It behaves like two circles with no overlap. So complementary events do not overlap. There's no, they are mutually exclusive, they are independent, they are disjoint. Okay? So because complementary events must be disjoint, we can use the addition rule as expressed this way, right? Where the probability of the event happening or not happening is equal to the probability of the event happening plus the probability of the event not happening. And since those are the only two possibilities, that probability is going to equal to 1, right? You're either going to get a good night's sleep or not get a good. You're either going to sleep last night or you didn't sleep last night, right? One way or the other, one of those things happened. So the probability of either one of those happening is 1. Okay? So when we add those two probabilities, they must equal to 1. So that can be very, very helpful, because that means that PA plus P complement of PA equals 1, which allows us to, if we only know one of those probabilities, it allows us to calculate the other very easily. If we know the probability of, let's say you're having a baby, it's either going to be a boy or a girl. So the probability of having a girl is PA, and the probability of not having a girl is the complement. If we know the probability of having a girl, then we can solve for the probability of not having a girl or having a boy. So the complement, which is probability of having a boy, is 1 minus the probability of having a girl. Okay? And that's because the probability of having a girl is equal to 1 minus the probability of not having a girl. So the complement really, complement events can be handled in this way. It can really simplify the addition rule. So let's look at these compound events where we're looking for A and B. We're actually looking for the area of overlap. In that case, we are going to use the multiplication rule. Okay? So we have these two outcomes, and there is an area of overlap. Okay? This is the probability of A happening. This is the probability of B happening. We're not worried about either one of those. What we are looking for is the probability that both are happening. Probability of A and B. And how we go about calculating the probability in this case depends on whether A and B are occurring in different trials, and so are kind of independent from each other, or they're occurring in the same trial in any order, or they're occurring in the same trial in a specific order. Okay? Specific order meaning we're looking for A happening before B or B happening before A. In all of these cases, we're still going to use the multiplication rule. We're just going to use it slightly differently. So that information is important to understand. So let's look at notation of the multiplication rule. We have the probability of A and B. Okay? A and B is the probability that event A occurs in one trial and the event B occurs in a different trial. So that's the notation with probability A and B. The different trials. A occurs in one trial, B occurs in a different trial. But if we want to look for something that happens in the same trial and in a particular order, the notation's going to look different. So probability of B/A represents, or line A, we're going to call it line A. So P line A represents the probability that event B occurs after it's assumed that A has already occurred. Okay. B is happening after A. So in that case, we have this intuitive multiplication rule. To find the probability of A occurring in one trial and the B occurs in another trial, we just multiply the independent probabilities. Okay? But if we are sure that B is coming after A has already occurred, right, then we handle it a little differently. Okay? So in that case, if we're looking for probability of A and B, where they're happening in a particular order, that's going to equal to the probability of A times the probability of B happening after A. Okay? B happening after A has already happened. Okay? And so it's important that you understand this B line A means that A is your starting condition. A has already happened. And so when we go to calculate this, because A is your starting condition, it will be the denominator of this particular probability. Okay? And we'll see that when we do examples. So let's look at the multiplication rule, an example of this, a simple example. So we have a classroom filled with third graders. Every child, we celebrate the birthday of every child. We want to know what is the probability that 2 children in the class will both have a birthday on a Monday. Okay. So the probability that a child will have, any child will have a birthday on a Monday can be expressed as probability Monday, right? P Monday. And since there are 7 days out of every week that any child birthday has to fall, right? And the birthday has to fall on one of those 7 days. The probability of a birthday on a Monday is equal to 1 over 7. Okay? There's one way that birthday on a Monday can happen, and there's 7 possible days. So the probability of having a birthday on a Monday for one child is 0.143. The probability that 2 children will have birthdays on a Monday is expressed as probability Monday and Monday. And we can use the multiplication rule to find that out. So probability of Monday and Monday is equal to the probability of Monday times the probability of Monday, which is 1 over 7 times 1 over 7. And that's equal to either 1 over 49 or 0.02. Let's do another example. And we're going back to our bipolar disorder table. What is the probability that a person picked at random from the 318 studied will have early onset BPD, early onset bipolar, and have no family history of a mood disorder? Okay. So we want to look, the starting condition is early onset bipolar. And then we want to look at, of those people, who has no family history. Okay. So in this case, we're looking for something called the joint probability. 2 conditions are occurring at the same time. Okay. And they're in a particular order: early onset and no family history. So we are looking for P early and no history, or PE and N, which is going to be equal to the probability of early onset times the probability of no family history when someone has early onset. Okay, so again, remember, early onset is your starting condition. And of those people, we want to know who has no family history. So let's put numbers in here. So the probability of early onset. Early onset, we have 141 people out of 318. So the probability is 141 divided by 318. The probability of no family history out of the early onset people. Remember, early onset is our starting condition. So it's going to end up in the denominator. Early onset is 141 people. Of those 141 people, 28 of them had a negative family history. So the probability of no family history among the early onset people is going to be 28 out of 141. We multiply those probabilities and we get 0.88. Okay. Excuse me, 0.088. Excuse me, 0.088.